Hi, so I thought I'd just share some of the work that I've been doing recently, and I've made this huge PowerPoint showing all the results from simulations that I've been doing. So the system I've been looking at is like a continuous magnet with this artificial spin ice, square lattice artificial spin ice on top. Basically, with this artificial spin ice, you can rearrange these four magnets in different directions, and you get these 16 unique or microstates. So I do what's called ferromagnetic resonance, where you basically take a magnet and you excite it with another magnetic field at a certain frequency, and that creates resonances. So some people might have seen these Chladni patterns, where you basically take a sheet and you apply a vibrational frequency to it, and basically you create mechanical waves in the material or the object, and the antinodes of the waves will, where there's no vibration actually happening, you get these collections of sand. So this basically can tell you properties of the material depending on what pattern it makes. So we're basically doing the same thing, but in a magnet, which is what these patterns are. So the idea is, by changing the arrangement of the magnet on top, we can influence the spin wave behavior. So if I apply a frequency at 1.8, we get a pattern that looks like this. So in theory, spin waves will be able to propagate along these channels. So if you notice this is a bit of an unconventional artificial spin ice. Normally we make these all the same size. Maybe if we look at these, you can kind of see that these two are more narrow than these two. And what this allows us to do is to put these into the microstate that we want by applying a field. If these were all the same, we'd have magnetic frustration, and we wouldn't be able to control the state. So by making this modification to the geometry, we're able to put these into any state by applying a certain magnetic field protocol. So basically what this PowerPoint is searching through the parameter space of all the simulations that I've done. So there's 256 unique simulations. So each of those 256 has some buttons on it. So these will show, if I click here, it will show you the same microstate and the same field magnitude, but it will change the orientation. So now we're seeing the same microstate but with a different field applied, and we can see what the actual system looks like here. And you notice how the resonances all change, and so do these spatial images. So this is basically a plot of what's happening inside the lower underlayer of this system. And these are like the Chladni patterns of that I showed earlier on the video. So we can change the orientation. So let's just jump into this so I don't have to right click. We can change the field magnitude, and this one just takes me back to what the previous one I was looking at is, and we can change the microstate. So this is a very nice way to search around the parameter space and compare things that have similar parameters. And as you can see, there's quite a lot of different things we can get out of this quite simple system. So obviously the spectra is changing and the spatial plots are changing, which means that they could be used to you can basically change the properties of this material by preparing it in a different state and then applying your fields in a different direction or a different magnitude. So you get this really rich spectra, which could be useful for some applications in magnetic computing or sort of magnon-based computations, or even maybe neural networks. But so that's the idea. But then the thing I wanted to talk about is how long did this take to make? So each of these 256 has 1, 2, 3, 4, 5, 6, 7, 8 plus 16, that's 24. 24 buttons for each one. So if I was to go in and individually link all of these to these interfaces, that would take a very, very long time. If we assume 30 seconds to assign each one, it probably is longer than that because mistakes are made, and I have to look up the exact number, because when I edit these, it's a pain in the arse to scroll through here and find the corresponding slide. So I created some lookup tables, which I use to, and then I can just type in the number when I select this button. So if I assume 30 seconds for each button, it should take 2.1 days. I managed to do this last night in about 6 hours. So the way I did that, so you notice that if I click on this, I think I found a mistake. Yeah, that's missing. So maybe I can demonstrate. So if I go to 4B10, so if I go to 45 4B5, so go back 45. Five 4B5. So I can copy these. Was it this one that wasn't working? Yeah. So these will share the same. Oops. These should share the same buttons. So now if I click there, I can now navigate to 5, 10, 15. Yeah, and I need to copy to here as well. So and presume, yeah. So that speeds up the process basically. So I just thought I'd just show a bit of my research and just a little bit of problem solving of how to speed up what you might normally think would take 2 days. Actually took about 6 hours, and if I was to do it again, it'd probably take a lot less because I developed quite a quick way of going through this. But yeah, so I'm probably going to add more functionality to this, but we'll see. But yeah, it's really nice for comparing, and you can just see there's really, really reconfigurable. You just put it in a different state, and you can see how different things can be. And yeah, hopefully this was interesting and useful.